Hello there and welcome back. So in this episode, I'm going to show you two things. The first thing is how to compensate for the slowness in the GPIO when it comes to visualizing the system clock signal on it, like we did in the previous episode. And then also talking about the system clock security. Now, I have had to switch from using the STM32 F303 discovery board to STM32 F407G discovery 1, and the reason is that the limitations of the F3 discovery board is beginning to get in the way of some of the things that I want to teach you. So first thing, this code is code you have seen already, and the only thing you haven't seen yet is this code here, right? Now, in the previous episode, I showed you how to route the microcontroller output signal onto PA8 and probed it with an oscilloscope so that you could visualize the system clock, right? And I told you that the slew rate, or the speed at which the GPIOs are able to perform by design, basically impedes the quality of the signal that you can probe on that pin. And it turns out that there is this HAL function called HAL enable compensation cell. And look at the note here. It says the IO compensation cell can be used only when the device supply voltage ranges from 2.4. So this is something you want to take note of. But basically, it helps compensate for the quality of the output signal when it comes to the limitations of the speed at which the GPIO pin operates. Okay, and also because I switched over to STM32F4, I had to make a change to the function HAL RCC MCO config call. So this remains the same, this also remains the same, but I had to change RCC MCO1 source HSE instead of sysclock. These are some of the subtle things you need to note when it comes to using different boards from what I'm doing. Also, if we go into the HAL RCC MCO config, you can see that the code, the library is already configuring the GPIO pin just as we did, right? So it said it's MCO pin, and if you go here, we should be able to see that that is MCO, that is GPIO pin 8, and the port is GPIO A. So essentially everything we did here isn't really necessary, so we can actually get rid of it. Okay, we can get rid of it, and then we just have to call the function after we have enabled the compensation cell. If your board doesn't support it, calling this function will basically let your code not compile. But because mine supports it, I can just click here, build. I don't want to generate code, so it builds all right without any error. And that is basically how you compensate for the slowness when it comes to the GPIO's speed at which it is able to turn on and off stuff. All right, now I will move on to the next thing I want to show you. All right, now the next thing I want to show you in this video is how to enable the clock security system. So essentially, the clock security system, which is also known as the CSS, is a feature of the RCC peripheral, which is used to basically detect malfunction of the external HSE, which is the high-speed external oscillator. And the CSS is an important feature in some critical applications where a malfunction of the HSE could cause injuries to the user. So imagine that you are working on a time critical firmware that demands that your timing is precise, right? And so you choose the HSE in your code, but for some reason HSE is failing. then the clock security system is going to kick in. And so its importance is proven by the fact that basically the detection of a failure is noticed through the NMI exception. So you remember when we were talking about interrupt, we saw the NMI, and I mentioned that it is so important an ISR that you cannot even turn it off. And so when the failure of the HSE is detected, the microcontroller unit automatically switches to the HSI clock, which is selected as the source for sysclock. And when you need higher core frequency, then you need to perform proper initialization inside the NMI handler. So let me take you to the source code. And I told you that, I mean, even though the code doesn't have to live in this .it_it.c file, that is how STM32 chooses to organize things. But we are not leveraging CubeMX, so we shouldn't be afraid to move things around or even delete what is in here. But for this exercise, I'm just going to do the same. So this is the NMI handler, all right? And this is what gets called when the CSS or the clock security system determines that or detects that there is an issue with the HSE clock source. It's going to trigger this ISR. By default, it just kicks into an infinite loop. It basically hijacks the processor and leaves it to do nothing. And I think this is a safety feature, right? So if your firmware demands precise timing and your clock source is misbehaving, then your firmware doesn't have to work, right? But you are able to actually intervene and respond. I mean, because we are not going to generate code, I'm just going to remove everything in here. The way you do that is you call HAL RCC NMI IRQ handler. This is a convention in HAL RCC where an ISR is called, and then there's a HAL IRQ handler that is called, like you call it. And inside this, we will see what we need to do. Inside of this function, we can see that it also calls a function called HAL RCC CSS callback. This function here is a weak function. Look at it, it's weak. And I've explained to you previously that when you see a function defined as weak, what it means is that yes, they are given a default implementation, but if you implement a function whose signature matches the same function, then what you have implemented in your code takes precedence over the default one. So I'm just gonna copy this one here, and then I'll come into our main, and then maybe down here you can just implement whatever you want to do. So when the code you need to write in here is code that you expect to execute when the clock security system determines that your HSE is misbehaving. And at this point, you can write code to fall onto any of the other clock sources like HSI. And if HSI is working perfectly and you need higher frequency, you can fall onto using the PLL engine to generate higher frequency clocks. And that leads us to the next episode where we will talk about the PLL engine. Thank you very much for watching this, and I will see you in the next video.